Mr. Kaziwa Steven. Students, good afternoon. I'm going to share those questions that you received. And in case you've not yet picked a question to do, you can do so. Pick a question, try it out. Today's session, we are going to look at calculating relative molecular masses only. Those are the first topics in physical chemistry. So there are like 4 topics. Pick any question that you like. Choose any topic that you really feel comfortable with. Prepare. You can write on a piece of paper. Then you take a photo. If you can type on a computer, it will be best. It will be the best. So I wish you well as we prepare to discuss, as we prepare to teach each other. I wish you I wish you nothing but the best. Okay, let me share questions on the screen. Then, in case you've already read those questions, in case you've already picked a question, feel free to prepare. I'm going to start picking people to present after 5 to 10 minutes. In 5 to 10 minutes, we should be ready to start. Okay. How many students can see my screen? If you can see my screen, just put up your hand. Just raise your hand if you can see my screen. If you can see my screen, just raise up your hand. Okay, those questions are in your WhatsApp group. So make sure that you can go there, check them out, choose the questions that you want to do, or the questions that you really feel comfortable with, and we can start preparing. Okay, we can put down our hands. So as we are preparing, I need one of you to lead us in a word of prayer. My name is Arjuna Bennett, and I'm a chemistry teacher. If you finish questions, I see Irene Indino. You've done some questions. That is good. So you prepare, you will present. Let's have a word of prayer. After praying, you present, and in case we see something which is not good, I'll guide you as students. Okay, who can lead us in a word of prayer? Who can lead us in a word of prayer? Thomas, are you raising up your hand like that?
Yes.
Okay, Thomas, you can pray for us. Pray for our session.
Let's pray.
Yes.
Oh Lord, guide us as we are starting through this session. May you continue being with us. Whatever we shall be learning, let's be able to understand it in Jesus' name. Amen.
Amen. Arthur, are you present? Okay, those who can present, I've seen Irene already telling me that she's ready. Those who think that they are ready, you can put up your hands. Then I see how we can present. Those who are ready, can we raise up our hands? Those who can present now, you raise up your hand.
Excuse me, teacher.
Yes, go ahead.
If you're ready, like you choose only one question in that topic.
For now, you present one question from a given topic, but later you can come in and present another one. But when you're presenting now, you just present one question from a given topic, that we get many people presenting. So are you ready to present now so that we can make you a co-host? Irene Indino, I see your hand is raised. Are you ready?
Yes, I'm ready.
Okay, now before I let in Irene to start presenting, I need to give you a few guidelines that will follow. Number one, you present using 2 or 3 minutes because they are basically calculations. You just tell us what you did, then you show us how you did your numbers. Then in case there is an error or a mistake, we will correct you. In case you have a question as a student, there is a session for questions. After every presentation, we have questions. So feel free to ask our presenters. Then in case you have a question which is directed to me as a teacher, you also say that my question is to the teacher so that I can come in and respond. So you can ask both the teacher and the student. Then for these questions that I sent, I need you to try them out, all of them. If you can do your best and do all of them, it is perfect. When you send them to me, I can respond. If you stuck on some given number in future or very, very soon, like today or tomorrow, still you can contact me. I will respond if you have a question or any other chemistry teacher. Okay, let's start. Irene, are you ready? Mr. Kaziba, can you make Irene a co-host? Yes, you are co-host. I'm going to stop sharing.
Teacher Bennett, yes. You have all the powers.
Kale. I'm going to stop sharing. Irene, you share your presentation. Thank you, Mr. Kaziba. Irene, you can present. You can share.
Okay. Good afternoon, good evening, ladies and gentlemen.
Good evening, Irene.
I'm Imran Irene. I'm going to take you through question number 3 specifically. I'm going to take you through question number 3. Though I almost did almost everything. So I'll take you through question number 3. Okay, that's question number 3. Question number 3 says, a sample of methylamine was placed at one end A, a 0.8 meter long glass tube. Then concentrated hydrochloric acid was placed at the other end B. So after some time, a white ring was formed inside the tube. The first question, they told us to write the equation for the formation of the white ring. So that was my equation. This equation is formed when in amines, if you have learned amines, the reaction of amines with amino acids. So that's where you find that as in this equation. Yeah, the reaction of amines with the amino acids. So if this was methylamine, which is H3NH2, it reacted with HCl, that is the concentrated hydrochloric acid, to give us methyl ammonium chloride. So that was my reaction, yeah. I'm sorry, that was a product of the white ring, methyl ammonium chloride. Then the next question, it told us to calculate the distance of the white ring from B. So So I say let the distance from end be bx, because the questioner told us to calculate the distance of the white string from end b. So the distance from end b, I let it to be x. Then the distance from end a, I let it to be 0.8 minus x, because the glass tube was 0.8 meters long. That means my distance from A to where the white string was formed, it will be 0.8 minus x. So for the case of the reaction, for the case of the rate, the rate of reaction. The rate of reaction is its length over time. It's 1 over time. So remember my length of this methylamine was put at end A. That means the length of end A from the white string is 0.8 minus x divided by the time. For that case, the time I used it because they told us after the same time. That means both, as in both the liquids use the same the same period of time. Then for the case of the rate of the HCl, that is the concentrated hydrochloric acid, its distance from the white string was x, then divide by the time that it took when it was traveling, that was t. So I got the rate of this methylamine divided by the rate of the hydrochloric acid is equal to the molecular mass of HCl, that is divided by the molecular mass of this methylamine over the square root. I think you guys are more comfortable with this formula. So from there, I did algebra because I substitute this. For that case, somebody may ask me where did the t disappear? Let me annotate. So this is what I did. Remember it was this divide by this. Are you getting? So if you are to get 0.8 minus x over t divided by x over t, you get the reciprocal of this x. You get the reciprocal of this x over t. So if you are to get the reciprocal, the t will cancel obviously, and we shall remain with 0.8 minus x divided by x is equal to the square root of 36.5 divided by 31. So from there, we apply algebra, and I got 0.384 meters. Yeah, I raised my case. That's the end of my presentation. That's number 3.
Okay, thank you very much. Before you stop sharing, you can leave your screen on. Since I've seen that you've already done numbers 1 to 3, I may request you to present all of them so that we can avoid taking a lot of time. But before that, students, any questions for Irene? Those with questions, can we ask Irene? Yes, Musa, you have a question. Can you unmute yourself?
Like, I beg her pardon on the calculation where she was showing us the square root. I've not understood it well. How the square root has disappeared.
Irene, is it possible to annotate and illustrate how your algebra was worked on?
Okay.
Someone need to understand.
It's obviously 36 divided by 5 over 31, you get the square root of that. And when they got the square root of 36, you have a calculator. Yeah, if you are to insert that into your calculator, 36.5 divided by 31, and you get the square root, you are going to get 1.1774. So you get the square root of the resultant, you're going to get 1.085. Are you getting? So from there, I got this x and multiply by this. This 1.085 is the product of the square root of 36 over 31. So that's what I came up with, Musa. So from there, I collected the like terms.
Okay, thank you very much. Thank you very much, Irene. There is another question from MP. Is distance the same as rate? Irene, can you respond to that or I respond to that?
I think Sherry will respond to that.
Okay, distance and rate. We have ways of fusion or rate of effusion is inversely proportional to density. And then later we end up saying that the rate of diffusion or rate of effusion of any substance is inversely proportional to the square root of, it can be square root of its density or square root of the then relative molecular mass. But then rate is the same as distance over time. So for you, when you're calculating, the rate can be, number one, distance over time. Is it possible to write it, Irene, on your screen? Distance over time, that can be the rate. That is distance traveled. It can be volume over time, that's the rate. It can even be the mass or the volume of the substance given over time. So it depends on what you've been given. And if you've not been given distances, if you've not been given volumes, you can even use 1 out of time to also get the rate. So for these calculations, you need to be very keen with how you determine the rate, because they rarely give you the rate. It is you to look for the rate. Okay, MP, is that okay? But MP, you need to first rename your, you have to rename your account here, because MP, is MP your name? We need your real name. Irene, that's
Yes.
it. MP, is that okay? So students,
Yes.
can I let Irene present number 1 and number 2 as we get more presenters? If you're ready, you've scanned your work or you've taken photos of your work, send a message, then I'll give you host rights.
Okay.
Yes, Irene, you can go ahead.
Okay. Number two says oxygen diffuses, that is 1.19 times faster than the gas X. So X contains 53.3% carbon, then 15.56% hydrogen, and the rest being nitrogen. So the first question was to calculate the empirical formula. So that's the thing. We start with the symbol. Obviously, I think most of you are so comfortable with that. We start with the symbol part of it, whereby remember the question they gave us carbon, hydrogen, and nitrogen, and the rest being nitrogen. That means all the composition was out of 100%. So it was a matter of you adding the 53.3 plus the 15.56, and you subtract from 100, then we would get 31.14. So that was the whole thing. We're just playing around the percentage things of them. So from there, you get the molar mass. This is what I did. I divided through by the atomic masses. So the atomic mass of this is, or carbon is 12, 1, hydrogen is 1, and this one is 14. So those were the products I got. So from there, I went ahead to get the mole ratio. I think everyone is very, very sweet about this mole ratio, whereby we have 4.4 to divide by. It's divided by the smallest figure. And my smallest figure came from the nitrogen part of it, which is 2.2242. So I divided through by 2.224, and these are the values I got. So from there, I've got the empirical formula. So I went ahead to get, the empirical formula, it was C2H7N. Yeah, that. Then they told us to get the relative molecular mass. Okay, remember the question, they told us oxygen diffuses 1.19 times faster than gas X. So if gas X diffuses, let me say, if gas X diffuses, if gas X, let me say, if gas X diffuses, let me say T times, that means this oxygen part will diffuse 1.190, because I've told us oxygen diffuses 1.19 times faster than gas X. So that is the algebra I applied. That's the algebra I applied, and I came up with that. Let me go back this my page. Yeah, this is what I did. someone asked me, why is it showing 1.19? Remember, oxygen was diffusing 1.19 times faster than, faster than gas X. So if this oxygen was diffusing T, let me say T times, and the other one was diffusing the T times, it's the vanishing T going to, because I don't want disorganized work. Okay? So that means this T that was here is gonna divide by this T, and we are going to remain with this 1.19 times that's seconds. So this is the resultant that I got after dividing the rate of oxygen and the rate of rate of X. So I came up with the square root of the molecular mass of X, and the molecular mass of oxygen, obviously, sorry, 32, because it's 16 times 2, you come up with 32. So after that, what I did in order for this square root to go away, I squared both sides. I squared this side, even I squared this side also. So when I squared this side, I multiplied it with 32. So, and I came up with 45.32 grams. Good. But for this case, they told us to get, the relative molecular mass. That means this gram wasn't required. Relative molecular mass does not have units. I forgot to conclude my answer. But the relative molecular mass doesn't have units. That means you're supposed to exclude the unit part of it. Then the next slide, they told us to get the molecular formula. So we have got the molecular mass. That means you are going to just equate, you're going to insert this N here, NH2. I think all of you know this, whereby you're going to get 45, N is equal to 45.32. So if I'm dividing through, I'll get approximately equal to 1. So my N will be equal to 1. So if I'm to substitute this one where N is, I'll come up with C2, H7, and N. So from there, they asked us to get the structure formulas of all that. So what I did, so told us to write the structure formula. The structure formula. So when I looked at this HN, I felt it was from amines. So I ran to the formulas of amines. So I was able to get ethylamine and dimethylamine. Those were the two structure formulas I was able to get from this structure. Ethylamine and dimethylamine. Now I'm done with number 1.
Okay, thank you very much, Irene. Can you go back to the previous page? Okay. I'm going to start with Serunjoji Wilson, followed by Nisima Vanessa. Serunjoji Wilson, can you ask your question?
Oh, thank you, teacher. Now the question I have, it's all about when we are getting the mole ratio and you find points. I would like to know the numbers you use to multiply in order to calculate the mole ratio.
Serunjoji, we are not hearing you well.
What I'm saying is that when we are calculating the mole ratio, there are certain times where you can get point. So I would like to know the numbers we multiply, like if we get 2 point something or 1 point something. Now there are certain numbers which
Oh.
Yes.
Okay. Thank you very much. Irene, are you in position to write what I'll be saying? Irene, are you there?
Yeah, I'm there.
Okay, you try to write what I'll be saying. So if you have 1.5 and 1, that ratio, 1.5 then 1. 1.5 you can always multiply through by a 2. So when you have 1.5 You always multiply through by. It can be 1.5. It can be 2.5.
Okay. So I've said 1.5.
It can be 3.5. You may find that you have 1.52, 1.5. So the numbers can be around 1.5. It can be 1.5, 1.6, 1.46, 1.47, 1.52, 1.53. So any number around 1.5, you multiply through by 2. Okay, that is number one. Number two, we may have a value like 1.33. You can put 1.33, 1.33. If you have 1.33, 1.31, 1.34, 1.36, any number around 1.33, we always multiply through by 3. Because when you multiply through by 3, it gives us a whole number. Now, those are the very common ones. But we can also have 1.25. Can you also put it down there? 1.25. It can be 1.25, 1.246, 1.247, 1.256. So something around 1.5. You multiply through by a 4. Because when you multiply through by a 4, you also get a whole number. Serunjoji, those are some of the most common values that you expected to get. If we say 1.5, if we say 1.33, it can even be 1. You get 1.33 plus 0.5. It can be 1.83. 1.25 can also be 1.75. So you need to know that. You need to know those different ratios that are common or that are expected. Someone sent in a message inbox and said 1.53, 2.33, 4.66, 1.23. I think I've answered your question. Most of them. Yes. 4.66, that's like 4.7. 4.7, you've seen what we do. We multiply through by a 3. Okay, we had 2 hands. Serunjoji, are you okay with your question?
Yes, I'm okay.
Vanessa, you're next. Unmute yourself and ask.
Good afternoon, everyone.
Irene, keep there. You're the one writing. Yes.
My question is on the next slide, which you had presented in getting the molecular mass.
Irene, go to the next page.
Okay.
Is on how she
Yes, to the next page.
how she calculated. Because our question, they gave us the rate of diffusion in terms of time, and then we know that the
Okay.
rate of
Yes.
1 over time. And so let me assume oxygen rate of diffusion of oxygen is 1 over time taken for oxygen to diffusion, even be corresponding to the same as gas X. And then if we substitute that 1 over
Vanessa, can you be a little louder? Vanessa, please, can you be a little louder?
Okay, the rate of diffusion of oxygen is going to be 1 over T and T, because they have in our question they have given us in terms of time. Yeah? So when I was going substituting our in that equation, substituting part of the equation, we are going to see that it's going to be corresponding with the root, as it's going to be root of the rate of diffusion of oxygen is going to be equal to the root of molecular mass of oxygen over rate of diffusion of X equals to rate of molecular mass, as in dividing. They are going to be corresponding because it is in time. It is in terms of year. So it has to be 1.
Vanessa.
Yes.
Sorry, I'm trying to follow your statement, but I need us first start from the beginning. I'm going to do something, and then you see if you're moving with the question, isn't it? Irene, can you stop sharing for 1 minute? Just stop sharing, then I use my screen briefly. You're going to share again. Okay, can we see my screen, all of us?
Yes.
Now, they said that oxygen diffuses 1.19 times faster than gas X. So they are giving us the rate. That means if I say that the rate, if my rate of diffusion of oxygen, let me say RO, is maybe, let me say R. Is that okay? Because it is the rate of diffusion, the rate at which oxygen is diffusing at. Then oxygen diffuses 1.19 times faster than gas X. So I say that rate of gas X, let me say it is X. These are the rates. But they have also told us that oxygen diffuses 1.19 times faster than that of X. So if gas X, if X diffuses at maybe at rate X, then gas O is, let me remove this, it is 1.19 times X, because X is the rate of diffusion of gas X, but this oxygen is 1.19 times, so it is 1.19 X out of X. So when we say rate of oxygen out of rate of X, which is equal to the root of relative molecular mass of X out of relative molecular mass of oxygen. Now in the question they gave us the rates, so we don't need to think about time and all those. So we replace RO with the rate of oxygen, which is 1.19 X. Then the rate of X is X, so we replace Rx with X. Then that becomes 1.19 X out of X is equal to what they put on the right hand side. Mx may be Mx out of 32, because they told us that the relative molecular mass of oxygen, since it's O2, it is 16 times 2, which becomes 32. So with that, these x's cancel out. That is why she ended up with 1.19 only. Vanessa, does that make sense?
Yes.
Okay, Irene, you can share. You can share again. So Vanessa, is it related to your question? Before I can remove my screen. Okay. Okay.
Okay.
Irene, you can share your screen again.
Yes, teacher.
Students, those who are ready to present, make sure that you take photos, very good photos. I will call upon the next presenter shortly after the next number.
So, teacher, should I go?
Or questions?
Should I go the next question?
Hold on. Students, any other question? I don't see any other hands raised. Irene, you can go to the next question.
Okay. Number two says a certain volume of gaseous hydrate of silicon, that is Si, silicon N, H2N plus 2, diffused through a narrow hole in 17.08 seconds. So under the same conditions, the same volume of carbon dioxide diffused through the hole in 20 seconds. It told us calculate the relative molecular mass of the hydride and also determine the molecular formula of the hydride. So before I begin, I first got the rate. Remember, the rate is always 1 out of t. So I got 1 divided by 17.008. I got 1 divided by 17.08. I'm sorry. Divide by 0.8. This is what I got. So I went ahead, also I got the rate of carbon dioxide, which is 1 out of t, and I got 1 out of 20. So our formula, which is the rate of this silicon divided by the rate of carbon, is equal to the square root of molecular mass of carbon divided by molecular mass of what? Of silicon. So this is what I did. Our rate of silicon was 1 over 17.08. Then I multiplied by the rate of, remember, if you are to divide by the rate of carbon dioxide, which is 1 out of 20, so I got the reciprocal. Yeah, I got the reciprocal and I came up with 20 over 1. So that will be equal to the square root of 44 over the mass of, the molecular mass of this silicon. So I square this side, I square this side, I square this side. After squaring this side, I divided 44 by this side. Are you getting? So I square this side to remove the square root. I brought this side, and the resultant of this, I divided it by, I divided 44 by the resultant of this, and I came up with 32.09 as my relative molecular mass. So from there,
excuse me, Irene, before you go ahead.
Yes, sure.
Michelle has an issue. Michelle, can you say something before Irene goes ahead?
I just wanted to inquire, can't we just say, like, we know that the rate is inversely the square root of the relative formula masses, but can't we, since they've given us time, we just say that the time is directly proportional to the relative formula masses of the compound given?
What I say.
Okay, that is good. That is very good, Michelle, and it also works. But remember, for these calculations, we are using Graham's law, and that law states that the rate of diffusion or effusion is inversely proportional to. So that means they are starting from the rate. So even you can do that. That time directly proportional to molecular mass, but you have to start from the rate. So that when we are marking, we see the word rate being inversely proportional to relative molecular mass somewhere, or rate being inversely proportional to the root of density. So you make sure that that main formula of the law that you're using comes out. But what you're saying is very correct, Michelle. So is that okay, Michelle?
Teacher, thank you.
Irene, you can go ahead.
So the next question, they had told us to get the, and we're getting the molecular formula of the hydrate. So if I'm to equate this SiN H2N plus 2 to 32.09, I came up with 30N is equal to 30. I got that. That means my N will be proportional to 1. Therefore, my molecular hydrate will be silicon 4 hydrate. So that's what I was able to get. And my structure, it was a tetrahedral shape. So that was the end of number 2.
Okay, Irene, we have a few questions. Joanita, can you unmute yourself and ask? before Joanita asks her question, students, do you have someone who is ready to present another number? Do we have someone who is ready to present? Okay, so prepare so that after this you present. So make sure that your photo is ready or your PDF scanned. Then we can go ahead. There is a question that Joanita has. So Joanita, ask your question. Then I have another question from Andrew. I will answer Andrew's question. So Joanita, go ahead. Ask your question. I don't think Joanita is asking a question. If Joanita you're asking, we are not hearing you. Then there is a comment here. Those comments we're going to come later, but this is very important because it's one of the things we're going to talk about. It is silane, not silicon 4 hydride. That is okay. Thank you, Andrew. Is there a formula of getting shapes? For there is when you're trying to get shapes, you need to always get to know bonding electrons and valence electrons, then those electrons that are not going to be used in bonding. So we always look at the number of atoms being produced by can I share my screen? I answer that question. Person asked about shapes. Okay. Now, when you want to get a shape of a compound, you always get to know the central atom. Now, in our case, we had silicon as the central atom. Now, atoms that are in the center, all the central atoms, they always contribute all their valence electrons. Silicon is in group 4, so it has 4 electrons in the outermost shell. So expect 4 electrons to be contributed by silicon, since it is the central atom or the central ion. Then we have ligands. Ligands are the atoms that are attached to the central atom. So that is hydrogen, but we had 4 hydrogen atoms. Now for ligands, all those non-metals that are attached, they only contribute bonding electrons. Bonding electrons, those are electrons that will be given out when bonding is taking place. If it is chlorine, chlorine needs 1 electron, so it just contributes 1 electron. If it's oxygen, oxygen needs 2 electrons, so it will contribute 2 electrons. Now for hydrogen, hydrogen contributes 1 electron because it needs 1 electron to become stable. 1 electron. But remember, we have 4 hydrogen atoms. So those ones will be 4 hydrogen atoms. They will produce 4 electrons. 4 electrons, but we say that 1 electron is coming from each atom. 1 electron from each hydrogen atom. You will write those ones. I'm trying to be very fast. So then we get the total of electrons available. 4 electrons plus 4 electrons, those are 8 electrons. How do we get bonds? Every bond is made up of a pair of electrons. Those are 2 electrons. So I divide by 2, and this one will give me 4 electron pairs. So that means I have 4 bonds. So I will think of what I studied from bonding and structure. We have silicon as the central atom. We have 4 bonds, 4 bonding positions, or 4 bonds available. There is hydrogen, there is hydrogen, there is hydrogens. Then you'd find that we have lone pairs. This is hydrogen, 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 then hydrogen. That's how she got the structure. But in case we had like 5 electron pairs, like here, if there were 10 electrons, those ones would give us, divide by 2, those ones would give us 5 electron pairs. Then you'd find that in our structure, we have a lone pair. Because you see, we have only 4 hydrogen atoms. But if we ended up with 5 electron pairs, you'd end up with a lone pair of electrons. So this is the procedure that we follow when we are forming structures. For the person who asked, I think I've answered your question. Person who asked, do you think you're now comfortable with how she got the structure? Okay, Ricky, I'm going to stop sharing my screen. Irene, share your screen again. Ricky, ask your question. Then Zahara, prepare, you're the one presenting next. Zahara, prepare, you're going to present after.
Teacher.
Yes.
How about when you have a charge?
Or when we have a charge.
For example, when they tell you to draw the structure of the carbonate.
Okay. Excuse me, Irene, stop sharing. I think I will still need my screen. Good. If we have a charge, now I'm going to summarize what we need when we have charges. Then after that, I'll call Zahara to start presenting if we don't have more questions. Now, a charge, a negative charge, represents extra electrons. A positive charge represents that there is, I would say, electron deficient, that molecule or that ion lost electrons. So if we have, like you said, carbonate, I'm there. We have carbon. Carbon is in group 4, so its valence electrons, all the electrons in the outermost shell, they are 4. Ricky, hope you're moving with me. Then we have 3 oxygen atoms. But before I got 3 oxygen atoms, I got oxygen alone. Now, oxygen alone has 6 electrons in the outermost shell, but oxygen is now the ligand. It's not the central atom. So for oxygen, it only contributes bonding electrons. So how many bonding electrons do we have for oxygen? Or how many electrons do we expect oxygen to gain to become stable? Anyone can respond.
2 electrons.
2 electrons, yes. So we expect oxygen to gain 2 electrons. So for it to gain 2 electrons, it must contribute 2 electrons. But then we have 3 oxygen atoms. That would be 3 times 2, which would be 6 electrons. But we say that 2 electrons are coming from an oxygen, 1 oxygen atom. Yes, these ones. Now, a negative charge represents that we have extra 2 electrons. So we just add 2 electrons. 2 electrons here. This will give us 4 plus 6 plus 2, that is 12 electrons. Divide by 2, those ones give us 6 electron pairs. 6 electron pairs. Good. Now, in case we have a positive charge, like ammonium ion, this is positively charged. Again, the central atom is nitrogen. So nitrogen will contribute all its valency electrons. Nitrogen is in group 5, so it contributes 5 electrons. Then we have hydrogen atoms. We've already said that hydrogen atom is the ligand, so it contributes only bonding electrons. How many bonding electrons are in hydrogen? By show of hands. You just speak.
1.
Just speak. Bonding electrons in hydrogen.
They are 1.
Yes, they are 1. But we have 4 hydrogen atoms. That is 4 times. That is 4 times 1, which is 4 electrons. But we have a positive charge. A positive charge means that it had to lose an electron. In this case, a negative charge was to add an electron. The negative charge. Check this part. Let me use a different color. Here, the negative charge, we added 2 electrons to give 6 electron pairs. But for the positive charge, we are adding an electron. Now, positive means we had to lose an electron. So we are subtracting an electron. Divide by, this is 5 plus 4, that is 9 minus an electron. That gives us 8 electrons. Divide by 2, this gives us 4 electron pairs. Now, when you start drawing structures, since we have 4, I'll put nitrogen here. 1, that is hydrogen. 2, 1, 2, 3. But it has a positive charge, so I can put this and fix a positive charge there. Students, are you seeing my screen very well? Then for carbonate, we had 6 electron pairs. So remember, for carbonate, each oxygen atom contributed 2 electrons. So I'll still write, hope you're seeing my screen well. I'll write carbon. Let me clear this place briefly. Erase. Again, we have carbon. Remember, we have 6 electron pairs, but oxygen contributed 2 electrons. So each oxygen atom has 2 bonds. So I'll have the first one. I'll have the second one. I'll have the third. Then we have 2 negative charges. I'll put them here. 2 negatives. That's a carbonate. I'm giving you general structures, but you can read and see how delocalization comes in and all the other things. Okay, I see 2 hands, Ricky and Lamek. Then Zahara, you can present. You can screen and start presenting. Ricky, then Lamek, then Zahara, prepare and you share your screen. Ricky, have I answered your question? Whether when we have charged particles, how we get their structures?
Yes, teacher.
Good. Lamek, do you have a question?
Yes.
Go ahead.
Okay, sir. What if you leave out the word pairs? Is the pairs a unit or what? What if you leave the word pairs out? Will a student be marked correct or wrong?
Here when we are writing pairs, when we are doing this pairs here, let me use red. This word here, pairs. Lamek, that's the word that you're talking about.
Yes, sir.
Okay. When we ask for the structure, we need only this structure, this one and this one, the final structures. So these ones is like side work. So you can do them, you can present them in the exam, then you draw the structure. It is well. But if the structure, the final structure is correct, then you don't always have a problem. You get your marks.
Okay, fine, sir.
Okay. Musasizipan Pade, then Mukisa Emma.
Teacher, what if they ask to explain that shape in words?
In words. You talk about the other one was trigonal planar. You talk about trigonal planar, then there are no bond. You talk about the number of bond pairs, the number of lone pairs. I've removed them, but the one of a carbonate was trigonal planar. The one of ammonium ion was tetrahedral. Talk about it's a tetrahedral structure with how many bond pairs and how many lone pairs. But that question of explaining the structure, it's rare. They always ask about angles. Then if they tell you to explain the structure, then you talk about the structure, how it is, the name, and the reason why it is like that. Questions of explaining structures, they come in when they are comparing. Maybe they want you to talk about angles that are coming in because of having lone pairs and bond pairs. But you always need to be careful. If you have lone pairs and bond pairs, they are focusing on those a lot. But if it is just a structure as it is and it's explained, then you need to talk about the shape, the name, talk about how it was formed using that math, and then you're good to go. But in case you have a question on that note, you can send it to me, then I can always respond. Then lastly, these gentlemen, there are 3 or 4 with a weird name. Your hand is raised, but I don't want you to speak because your name is funny. And I see you're like 4. So who is going to ask a question? The one with a cape? Okay, ask. We are not hearing you though. We are not hearing you. Mukisa.
Master, my question is,
students. Yes.
Like one of the question is, you have talked about it when you are having lone pairs. Hello?
Yes.
When you are having lone pairs, like how does the structure change the alignment of those hydrogen or oxygen atoms? How do you align them on the central atom when you have the lone pairs and without the lone pairs?
Yeah.
Okay. Briefly, when you go back to your notes, how your teachers taught you, we have 2 positions. We have the axial position and the equatorial position. They taught you that axial positions are very stable. Axial positions are the, let me start writing. If I have this carbon and I have a lone pair, I'll put one hydrogen here, another hydrogen here, another hydrogen here, and the lone pair will be up there because this is the axial position. These are the equatorial positions. Equatorial positions are more stable. They make the structure very stable. When you have, let's say you have X, then I have a number here, I have something here, I have something here. Then you find you're meant to put your lone pair here, then you put another structure here. So it goes back to the number of atoms that you have and the number of lone pairs that you have. So for now, I may not say that we consider this and we consider this and we consider this. For every structure, depending on the number of electrons that we have and the number of lone pairs that we have, they give us a picture of the diagram to draw. But those are some of the examples. You see that you put it on one side. These ones, you see like these lone pairs here, it is on the upper end, which is the axial position. This one has been put on the upper end. But depending on the number of lone pairs that you have, you can find that you're putting them on the upper end, on the lower end. Then if it is axial equatorial, you need to read that. These are the equatorial positions. Briefly, these are the equatorial positions. Look, these are the equatorial positions. Then these ones here, this one and this one, these are the axial positions. So depending on the number of electrons available and lone pairs available, we find that you're putting lone pairs in the axial positions, or you're putting lone pairs in the equatorial positions. But we've said that we start with equatorial positions, then we go to axial positions depending on the structure. Okay, I request for your favor because I don't have enough power. Excuse me, sir, could you help me write question 3 because I'm not in the group. Okay, Zahara, can you start presenting? Zahara or any other person.
Yes, teacher.
Again, if you're ready to present, I see another person ready to present. Zahara, you share. Then hold on. Brian, you're the next one. Brian, you're presenting after Zahara.
I need the pause. Teacher, make me the co-host.
That's what I'm doing, Zahara. You're not yet co-host. Good. Can go ahead.
Can you view my screen?
No, I can't. I can't.
Zahara, not yet. We cannot see your screen. Sorry for coming. Zahara, we cannot see your screen. Can I call someone to present as you're preparing, or we give you some time?
Give me some time.
Yes, it has come. I see it coming.
All right, members, my name is George William. George William, I'm from the same. All right, I would like someone to call me with number 5.
George, number 5, you want people to do it for you. Let one of you will do it. 11.25 grams of an organic compound P, complete combustion needed, that of carbon dioxide and that of water at STP. Given that P is a vapor density, can you send it to my inbox right now? That as people are presenting, then Zahara, go ahead and present. Liam, send it to my inbox so that as Zahara is presenting, we can also work on it. Brian, prepare. If Zahara fails, you present. Zahara, are we still struggling so that I make? Yes.
Hello, my name is George William. sorry to interrupt your seminar. Like,
Glad
I'm
you
not
know
among
what
the.
it-
I'm not supposed to present, but I just have a simple question I would like to present. Number 5. If any of you please can
Yeah.
help me with it, please, I'm requesting some help
Excuse
on number
me,
5.
DM. Yes, I've said send it to my inbox right now. Then you can allow the presenter to continue.
What should I do?
Send me a message in my inbox, then I send you my email. Yes, Zara, go ahead, present. Liam, send it to my inbox right now.
Oh my.
Brian, prepare to present. I think Zahara is failing to share. Zahara says something if you fail to share.
My picture's been deleted. Let someone else present as I take them.
Okay. Okay. Brian, present. Brian, I'm going to make you a co-host, then you can present. Brian Joshua,
Yes, teacher.
I've made you a co-host. You can present.
All right, all right. Can you get me very well?
Yes, we are hearing you very well.
Okay. Are you able to see my screen?
Yes, it has come.
All right. So, thank you for the opportunity granted me. I'll be taking you through question 1, and that is part of the polygon properties. It's unfortunate that I don't have the question here, but if someone can help us with that question, it will be good. That's what I was able to summarize out.
Okay, I've seen you've summarized 2 questions. I'll give you time. Let me see. Colligative property number 3, then radioactivity number. Which number of radioactivity?
Question 1 is question 1.
Okay. Then you go ahead.
Then radioactivity still question. Okay. This question.
Yes. Okay.
Can I proceed?
Yes, go ahead.
So in this question here, we are given mass of benzene and mass of carbon tetrachloride. So according to the way I analyzed the question, I was able to find out that benzene was the liquid and the carbon tetrachloride the solute. So we see that this solute, the carbon tetrachloride, is being added to benzene, and there will be a depression in what? In the freezing point, because according to the question, they told us that the freezing point of benzene reduced, meaning that it was a depression, rather a decrease in freezing point of what? Of the pure solvent, which is benzene. So I said that 50 grams of benzene dissolves 0.91 grams of carbon tetrachloride, which is the solute, because it is the solvent which dissolves the solute. Someone says it's not able to see what I'm presenting. I don't know what could be the problem about it, the network. I can't tell. I don't know whether all people are seeing what I'm trying to present. The question I'm presenting.
I'm seeing, hold on, Brian. I'm seeing what you're presenting. Students, if you're seeing what Brian is presenting, can you raise up your hand? They need you to zoom in.
Okay,
We can see it, but it's small. Yes, like that. Is it possible to turn your phone landscape?
I turn it is impossible,
Like
sir.
landscape. It is not okay. Then we will handle. Keep zooming in and out so that all people can see very well.
All right. So I think I'm good to go.
All right. So I was like, we were given mass of benzene, and benzene being our solvent, it dissolves the solute, and the solute for this case is carbon tetrachloride, and the mass of the solute also was given. So I'm saying that 50 grams of benzene dissolves 0.91 grams of carbon tetrachloride. What about 1,000 grams of benzene will dissolve the 0.911 times 1,000 over 50 grams of carbon tetrachloride. So when I try to compute, I got 18.22 grams of carbon tetrachloride, meaning that is the mass of the solute, which was dissolved by 1,000 grams of benzene. Then they told us in the question that the freezing point reduced to 0.659 degrees Celsius, meaning this is the depression or the decrease which was caused by the other mass we found, the mass we are just from finding. So I'm saying that 0.659 degrees Celsius is depression caused by 18.22 grams. Then what about the 5.5? Now this 5.5 is the freezing point constant. And we all know that freezing point constant is a decrease or depression in freezing point, which occurs when 1 mole of a non-volatile solute is dissolved in 1,000 grams of what? Of a solvent. So this 5.5 degrees Celsius is the freezing point constant of what? Of benzene. So they told us to find what was it the molecular mass of carbon tetrachloride. So the molecular mass of the carbon tetrachloride, of course, will be in the what? Will be in the freezing point constant, because we said 1 mole of the what? 1 mole of the non-volatile solute being dissolved in 1,000 grams of the what? Of the solvent. So when you compute, we get 152.1 grams of carbon tetrachloride as the molecular mass of what? Of carbon tetrachloride. I'm done with that question, unless when someone has a question, or unless when a teacher has something to supplement on that. Okay, I can see the teacher has tried to share the question. Those who ask me for the question, you can write in the chat.
Okay, those who need the question, it's in the chat room. Thank you very much, Brian, for that presentation. I'm going to give you a chance to also talk about your number 1 of radioactivity, and then those with questions, we can put up our hands. In case you have a question, put up your hand. Then there is a question here. How do you comment on your answer, Brian?
About the comment, I will request the teacher tell me that, but you know, I was in the I ended up forgetting that.
Okay, it is okay, Brian. So when they talk about comment, they need you to observe if there was association or dissociation. Now, when you look at the relative molecular mass of carbon tetrachloride that you have, it is 152. So you had even to conclude. So you have to calculate the normal relative molecular mass of carbon tetrachloride. Can I share my screen briefly so that I can talk about it? So stop sharing. Yes. Yes. Now, when we look at carbon tetrachloride, it is let's all do it together. Carbon tetrachloride. So carbon is 12, so that is 12 times 1 plus chlorine. Atomic mass of chlorine is 35.5. That will be 35.5 times 4. Those with calculators, what are we getting?
154.
154. So yes. Did we add the 12? So that would be 12 plus The total reactive molecular mass is 154.
154.
154, everything.
Yes.
Now, thank you very much. Now, Brian had an answer of 152, 52.1. Brian, that's what you had, correct?
Yeah.
Good. That means that you see that in Brian's experiment, he got a value which is close to the real relative molecular mass of carbon tetrachloride. So in that case, we say that there was no association or dissociation. If Brian had an answer like 310, if he had obtained a value like 310, and you see that the relative molecular mass of carbon tetrachloride is 154, but you find that in his calculation he had 310. You realize that 310 is the same as 154 times 2. 154 times 2, that is 308, which is also close to, hold on, which is very close to 310. So if we have that case, we say that when they say comment, you say that there was association of carbon tetrachloride in benzene. Because here you see that two carbon tetrachloride molecules combine together to give us a bigger one. We call them dimers, to give us a dimer which is 310. So in that case, on the part of write a comment, you say that there was association of the solute in the solvent. But in our calculation, there was no association and there was no dissociation. So Brian, I'm going to stop sharing my screen. You go ahead, share, and you do the next number of radioactivity. Then those with questions, hold on. Who is this with the camera on? Yes, let me post the question. Which question is that, Brian? Number 1 under radioactivity.
Yeah, it is number 1 under radioactivity.
Okay, I'm going to post it in the chat. Students, those who don't have it, I'm going to post it in the chat room. So Brian, you can go ahead.
All right, thank you so much, sir, for that insight and supplement. I hope everyone has gotten that. So we proceed to our next question. This question is all about the radioactivity. And on this part here, we were given the half-life, and they were telling us to find the decay constant. So from the expression, half-life is equal to 0.6931 over lambda. This is 0.6931 is from natural logarithm of 2. That is the 0.6931 when rounded off for decimal places. So from this expression, you see that we can able get what? We can able get the decay constant. Since we have the half-life, we can now get the what? The decay constant. And the units here, I said per day because we are dividing with what? We are dividing with half-life. And half-life is in days. So I got my answer 0.0231 per day as the units for decay constant. Then the other part of question B, we were given some, were they masses? We were given some value, and they told us that they gave us the initial value and a certain value at time t. That's why you're seeing any note. That's the initial. Let me call it mass because I'm not sure about the question now. Apparently, I don't have the question here. So I called it N naught, and then the other 300 I called it NT, and they want us to find time. And since you already have the decay constant, you can able to find time from the expression natural logarithm into N naught over NT is equal to lambda, which is the decay constant, time with the time. And since we have N naught and NT and the lambda, we can able to find time. And our time we got as 120 days, because this is time, but in days. I think that's what I can say about that. Unless the teacher has something to supplement, or unless we have another question.
Okay. Thank you very much, Brian. I see Ricky and Michelle. Their hands are raised. Ricky, Michelle, one
Teacher.
of you, we can ask our questions.
Yeah, teacher. My question is,
yes, Ricky.
What's the difference between because when they say colligative property, one of them says the solid should not associate in the solvent, and the other says the solid should not react with the solvent. So what's the difference between reacting and associating?
Okay, thank you very much. Let me respond to Ricky before Michelle can ask. In colligative properties, we know that we have solutions. Solid particles are mixed with solvents to give us solutions. Now we expect that solid particles should not associate. That's the word that we use. Solid particles should not associate or dissociate. Listen to those words very well. Solid particles should not associate or dissociate. Then we say that solid particles should not react with solvent particles. Have you heard the difference?
Yes, teacher.
Okay. Have I answered your question now?
Yeah. Thank you so much.
You're welcome. Michelle, can you ask your question?
Yes, teacher. Teacher, you said that on that very part of explaining, like your answer meant to me. For example, if I got my new value as maybe 460, which is 3 times. Yeah? Teacher, will I have
Which value?
that
Michelle, which value?
the value was 154 grams. But when we calculated, we had 152. So I calculated. In case I calculated and
Michelle, I'm not hearing you well.
Hello, teacher.
Yes.
I was trying to say that
You calculated and you got
100 and 400. And my original value, the normal value is supposed to be 154. Now, when I'm putting we'll have to say that there is association because the two carbon will I set to read for this case?
Okay. Michelle, is it possible to type your question in the chat? You're breaking, but in case someone heard that question very well, you can just read it for me because I'm not hearing you very well, Michelle. You're breaking, but I heard that if you calculated and you got like 400, am I right? Did I hear correct things?
Yes, teacher.
Yes. If it is like 400, that means that the solid particles associated. Because when they are associating, they can associate in pairs or in that is 2 associating together. They can be in 3 molecules combining together, 4 molecules. So numbers can be very big. Numbers can even be a little smaller. But if they dissociate, that is when they break down. Then we expect the relative molecular mass now to be very small. But if you get 400, again, you say that there was association because it's a value which is bigger than the 152 or the 150 that we expected. Okay.
Excuse me, teacher.
Yes.
Yeah. I wanted to present my last solution, but before I can before I can present, I just wanted to an association. I think that's was the question from the person.
Hey, it's okay, go ahead.
I don't
Hey,
know
go
whether
ahead.
I'm free to person or you're technical. All right.
Yes, you
now
can
for
respond.
association, you see that association, solid particles, they come together, and as they come together, it increases the number of solid particles within a solvent. When solid particles do associate, or when association occurs, the number of the solid particles within a solvent decreases, and we know that a colligative property is directly proportional to the number of the solid particles present within a solvent. So that means that when association occurs, it will lead to a decrease. It will lead to a decrease in what? It will lead to a decrease in the colligative property, and the molecular mass will do what? Will increase. Then when dissociation occurs, we say that the solid particles will separate or will break into ions or particles, increasing their number within a solvent. And this will lead to an increase in the colligative property and a decrease in molecular mass, since colligative property is directly proportional to the number of solid particles present in a solvent, and inversely proportional to what? And inversely proportional to what? The molecular mass. That's what I just wanted to comment or to inform.
Okay. Thank you. Thank you very much, Brian. Yeah. And thank you very much. I've seen many people posting the answers. I've seen many people trying to post those correct answers in the chat room. So lastly, Brian, can you present your last answer? And then lastly, Zahara, are you ready to present? Or Zahara is no longer here? Did you organize your work?
Yeah, I've organized it.
Do you think you're ready?
Yeah.
So after Brian presenting his last number, I see mass spectrometry, you will present, okay? Brian, you have like 6 minutes. I see our time is really getting finished. Okay, right, Brian, go ahead. Right. Zara, I'm going to make you a co-host also.
All right, thank you so much, sir, for the opportunity granted to me. So I'm discussing my last.
Brian, we are not hearing you. Brian, we are not hearing you. Okay, Zahara, prepare to just get ready. Zahara, you can share your screen and start presenting. Then Brian will come back later. And in case you also have your work ready to present, just send me a message that your work is ready to present, so that after Zahara, someone else can present. Brian has come back.
I'm really
sorry. Brian, go ahead.
What had happened, but it was all about networking. So I was like, that the mass spectrometer is passive evacuated through the vacuum pump to ensure that there is no resistance movement of gaseous ions by air particles. Then the sample under investigation or to be investigated is introduced in the atomization chamber, where it is vaporized from gaseous atoms. Then the gaseous atoms formed are then subjected to a beam of fast-moving electrons from the hot filament. The electrons will collide with the gaseous atoms and cause ionization to form positive gaseous ions, i.e., I said if you have, let me say, if you have gaseous atom M it undergoes ionization. Of course, ionization, we are forming gaseous ion. So it undergoes ionization, forming the M gaseous plus one, rather M gaseous ion and the electron. And I said where M are atoms of the sample, the gaseous atoms. So after ionization, we are forming ions. Then the gaseous ions are then accelerated through the electric field at uniform velocity to enter the magnetic field. In the magnetic field, the gaseous ions are deflected according to mass to charge ratio. Therefore, the magnetic field is varied such that ions of the same mass to charge ratio hit the collector at the same time. Once ions hit the collector, they produce an electric current which is detected, amplified, and recorded as a line peak on the mass spectrum. So the height of the line peak is proportional to the percentage abundance of the isotope that produced the ion in the sample. Then from there, we go to treatment of results. So we are saying that assuming a sample had two isotopes with percentage abundance A1 and A2 corresponding to masses M1 and M2 respectively, RAM, which is the relative atomic mass, will be equal to the summation of the isotopic mass times abundance over total abundance. So we are saying that relative atomic mass is equal to M1 times A1 over the total abundance, which is A1 plus A2, then plus M2 times A2 over 1 plus A2. So that's how we can determine the relative atomic mass of an element using mass spectrometry. Then the next part was asking that what is meant by the term relative intensity. Relative intensity is simply the height of the line peaks of the different isotopes.
Brian, before you go ahead, someone is asking.
Yes, please.
Yes, someone is asking you if you have a diagram for that explanation.
The diagram I don't have it right now, but I can get it if in case the person wants it. I have it, but not in soft copy. It is in rather not in hard. Yeah, it's not in soft copy, but I have it in hard form or hard copy. I can get and send the person if in case the person wants it. But apparently, I desperately just using what.
Okay, can go ahead.
All right, thank you. So the other question was explain what is meant. Now explaining what is meant is that it does not only require the definition, but it requires you to talk about everything about the particular or the required let me say definition. For example, they say that explain what is meant by what relative intensity. They say that this is the height of the line peaks of the different isotopes on the mass spectrum. That's what I know about relative intensity. Then question is 3B. Remember number 2. They gave us some information, but instead of giving because in most cases they give in most cases they give abundance, but for this case they give us what total relative intensity. Total relative intensity can work as the same thing as relative abundance. Can at the same time work as what? Relative abundance. If in case it's not given, you can use the relative intensities. So first of all, I go to the summation of all the total intensities. Then from there I say relative atomic mass is equal to the summation of the isotopic mass times relative intensity over the relative intensities. So I had to compute or to manipulate I had to manipulate the isotopic mass times the relative intensity of over total relative intensity for the respective isotopes given, because they were like isotopes of A. So when I computed and manipulated, I was able to come up with the relative atomic mass of A as 55.9111. No units, no units. That is it. Thank you.
Thank you, Bran. Students, these questions are meant to be used while you're practicing for your papers. We are looking at how to determine relative molecular masses, those topics that involve determining relative molecular masses. So take some time and do all those numbers. Of course, I'm going to call upon the last presenter for today. In case you have a question or questions before I call in the last presenter, you can go ahead and ask. Michelle says Bran has been breaking, so they didn't hear you very well. Musa M, do you have a question? Or you want to present? But I have a presenter. Musa M, ask your question, then I.
Okay, sir. Like for me, what I was asking about, it is about relative intensity. What if I'd say that it is the ratio of isotopic masses, or the proportion of isotopic masses in a given element? Will I be right?
Yeah, when you say proportion or composition, proportion is okay, because you need to remember that when you talk about relative intensity, they are looking at how, I would say, the masses or the peaks representing the composition of the different isotopes. So that is also fine. Your thinking is also okay. Just that you need to make sure that when you're presenting it, you write very good chemistry. I see Zahara is sharing. We can see if Zahara can present. Yes, Zahara. I see your work. So Zahara, you're the last presenter for today, but girls and boys, you're requested. Yes, you're requested to do all those numbers on your own.
So,
yes, good evening, Zahara.
Presenting number 1. Okay, the question was 15 cubic exploded with 120 cubic centimeters of excess oxygen, cooling the residual gas when passed through potassium hydroxide solution. 45 cubic centimeters of the residual gas remained. And they're asking me to write the equation of the reaction that took place. I hope everyone is seeing it.
Zahara, we are not seeing you. Zahara is not there. I need to call upon the last person to present, because Zahara seems to be on and off. Many people sent me messages that they are ready to present. Okay, I'm going to post the question in the chat room, but Zahara is not here. So let me hold on and see. Those who are ready to present, can I call upon another person? Because Zahara has disappeared again. Okay, Zahara has come back.
Okay, so to get the volume of oxygen that reacted, we get the excess oxygen that was there initially minus the volume of residual gas that remained. And that was giving us 70.
Excuse me, Zahara. Zahara, you
cubic centimeters.
went off briefly. You've just come back. like you kept on presenting. You went off, you've just come back. So you need to present from the beginning.
Yes.
You went off, so it's better you present from the beginning.
I need to restart. But teacher, that was the first part.
Okay, go ahead.
The question. I think people have the question.
Yes. So go ahead, Zahara.
Read it.
Okay, go ahead.
In the question, we are given the excess, which was then they cooled the residual gas to room temperature, and then they got 90 cubic centimeters. And then they passed through potassium hydroxide solution. 45 of the residual gas remained. But then we all know that potassium hydroxide solution is to absorb carbon dioxide. So if we are to get the value of oxygen that reacted, we are going to get the excess minus 90 minus 35, giving us 25 cubic centimeters. Then for the other part, they're telling us to calculate carbon dioxide that was formed. But then after cooling the residual gas to room temperature, we remained with 90. Cooling this is just remove, I think, water crystallization, and then leaving us with 90 cubic centimeters. This 90 contains some oxygen and then carbon dioxide. So when they pass through potassium hydroxide solution, meaning they are absorbing of them. So to get carbon dioxide, that was produced, we are going to get the 90 minus get 45, so 1 cubic centimeters of X. But then I already have the X, which was the hydrocarbon, which and I was given its value, which was 15 cubic centimeters. So I'm going to say I'm talking to myself.
Thank you very much, Zahara. Any question or questions before I say bye to everyone? Because Zahara's network was not very good. Someone says they didn't get anything. So Zahara, make sure that you send your work in our chat, because some people didn't hear you very well, yet you are doing a very good number. Michelle, you're the last person to speak.
For example, for such questions that require us to write equations, for example, we can have CH and it has an oxygen, so we shall write it as 2X HY or Z plus oxygen. That is that I found a problem with balancing such equations.
Yes.
Would you
Okay.
help, like, how
to balance them?
Yes.
Okay, thank you. I'm going to see if I can talk about it. Then lastly, Musasizi.
And my question is about the previous number of relative abundance.
Musasizi.
Yes, teacher, I'm speaking. I found on the previous number that we did.
Yes, we are hearing.
The previous number that we did about relative abundance, I found the question somewhere where they had given only the masses of the isotopes, like chlorine 35, chlorine 37, and they were asking for the relative abundance.
Yes.
Could you please clarify on that one?
Okay. Then lastly, Serin Georgie, if you ask many questions, I'm going to answer a few of them, depending on the time. Serin Georgie Wilson, you're the last one to ask a question.
Teacher.
Serin Georgie, we are not hearing you, so I'm going to answer people's questions, then I stop from there. Wilson?
Teacher, I'm speaking.
Yes.
So, Master, I just need that so that when
Wilson, we are not hearing you. Okay, I'm going to answer one last question. Wilson, I'm going to answer one last question. Then other questions will come through next time when we meet. Maybe I'll talk about the question from a gentleman. Then there was another question from a lady about balancing. I think I'll balance that next time. Then the question from a gentleman, I can summarize it right now because I know it's longer. Okay. Are we okay with that? Can I summarize it very fast, students? If you can follow it up, just say yes. Then I summarize it very fast.
Yes.
Okay. So if they give you just masses and they don't give you relative abundances, there is give us chlorine 35. They also talk about chlorine 37. Then they always give us the relative atomic mass, which is 35.5. I'm going to do this, then we'll end from there. Then the equation, my dear friend, the lady, will start with it next time we meet again. So from here we have masses, but we don't have abundances. So we just let these abundances, we just say let the relative abundance of maybe chlorine 37 or 35, depending on what you like, be X%. Now when I say X%, that means that the total of the abundances is 100. That means that the abundance of chlorine 37 will now be 100 minus X%. You see that now I have abundances, yet they are not given me abundances because I'm using percentages. So when I say chlorine 35 is X, then chlorine 37 will be 100 minus X. When you add them, you get 100. You know that the total of abundances is always 100%. So that note, we start. We do the normal things. Relative atomic mass is equal to the summation of all isotopes, but we get the abundance times the isotopic mass out of the total abundance. Don't look at my simple forms. I'm just using A to represent abundance, then M to represent isotopic mass. So that will be 35.5, which will be equal to, it will be atomic mass. If I go to this chlorine 37 here, this one 35, it will be 35 times, what is its abundance? Just unmute yourselves and speak. Abundance for chlorine 35?
X.
Good. This is out of, then plus 37. What is the abundance of chlorine 37?
100 minus.
Unmute yourselves and speak. Yes, 100 minus X. Everything is out of the total. The total is X plus 100 minus X, which will also give us X. That will give us 100. So later 35.5 will become 35 X plus 37 out in brackets 100. The person who asked, and all of you, can you finish this mathematics now? Since you have this, get the value of X out of 100. Those who can finish, then you get the value of X, that would be the relative abundance of 35, then 100 minus X, that would be the relative abundance of
X is 75, then
chlorine 37.
Teacher.
Okay, so that is it, students. Thanks for attending. Thanks for being good students. I see someone saying teacher. I hear someone saying teacher. Teacher, can you say something? What's up?
Teacher, the 30. How about when I use X on 37? Am I wrong?
You're also fine.
Okay, teacher, thanks.
Okay. You're welcome. Nambi Victoria, are you praying for us? Nambi, say something and pray for our evening.
Teacher, please elaborate on the 19 centimeters cubed of the residual gas. Residual gas, 90.
Yes.
What does it contain except carbon dioxide?
Okay, cooling to room temperature, that the residual gas occupied 90 cubic centimeters. We always have carbon dioxide. Then we have water vapor that is always formed. So many times the water can cool. When we reduce temperatures, we expect the water to condense, form water. But sometimes some water molecules may not have cooled down. So initially, we have that residual gas as carbon dioxide. Then we have unreacted gas. We may have some oxygen that did not react, the excess oxygen gas. So if we have excess oxygen gas that did not react, it is also part of the residual gas. Then in case the water did not condense properly, it is still there, but we believe that water has condensed in this process of cooling temperatures to room temperature. We expect that all the water vapor should condense to liquid water, but we'll be having excess oxygen that did not react, then the carbon dioxide gas that was formed. Okay, can you pray for us?
Let's stand ourselves for a prayer. Dear Lord, I want to thank you for our lives, for this section, for the teachers. Dear Lord, we pray for your forgiveness where we have wronged you. We pray that you may have mercy on us. Father Lord, we pray that you may bless our teachers and our discussants and give us the zeal to continue being hardworking. We pray this through Christ our Lord. Amen.
Amen.
Okay, thank you, Vanessa. Amen. And nice evening, students. Make sure that you do all those numbers before we meet again. Bye.